Okay, so applications of double integrals. We've already seen one application of double integrals, computing volumes, right? You had a lot of those kind of problems on your third exam. Another geometric application is finding areas of surfaces. That's going to be done in section 12.6. In this section, we explore physical applications such as computing mass, electric charge, center of mass, and moment of inertia. Okay, and they also mentioned that you can use double integrals to talk about probability density functions of two random variables. Now, that's my wheelhouse, probability density functions, because my PhD is in mathematical statistics. But I'm going to focus on the other applications. You can look at the probability density functions and look at that, but you have to know statistics also for that to really make good sense. I'm going to focus on some other applications, something that we would see perhaps in engineering or some of the other sciences. And there's one application about finding charge density, okay, over a region. And they do an example 1 in section 12.5. And I'll let you look at that. I think the problem in the homework has a help video for that. I want to focus on density and center of mass for our lecture here. So let's talk about density. Okay, so how many remember that density is mass divided by volume? How many remember that definition for density? Okay, Yeva recalls that. And indeed it is. But in section 12.5, we extend this idea to, well, density over a lamina. So a lamina is a plate-shaped object, okay? It's, I mean, I'll show you a picture here of a lamina, okay, in figure 1. So there's a lamina, and there's a point on the lamina. And if you think about a lamina with variable density, the density of the hold on here, yeah, the density of the lamina, okay, changes throughout the region. So we're not talking about a lamina with constant density. Well, it could have constant density, but we want to allow for the lamina to have density throughout the region. How many maybe have dealt with density? And by the way, the units, I'll highlight this here now. The units we're talking about are mass per unit area. Has anybody encountered this in an engineering or physics class? Density of a lamina? All right, well, maybe not yet. Okay, no problem, no problem. Well, let's keep going here. So if density is mass divided by area, then mass would equal density times area, right? Mass would equal density times area. And what we're interested, of course, is in figure 2 here. If we wanted to find the mass of that lamina, well, we would have to compute the density at each little point on the lamina, and they break up the lamina into like a grid there with rectangular regions, okay? And we would have to find the total mass of this region in figure 2, we'd have to find the mass for each of the little subrectangles. That means we would have to find the density. We'd have to pick a point in each subrectangle and pick a point in the subrectangle, compute its density, and at that point, and multiply by the area of the little subrectangle, and that's going to give us a little mass. So picture computing a bunch of little masses in each of those little rectangles that overlay the region D, would overlay that orange lamina, and then adding up the masses. Well, that would give you then the total mass. That would give you an approximation to the total mass, which would be a double integral. But of course, as you take smaller and smaller subrectangles of the mass, then you're going to have a better and better approximation of the total mass of the lamina as you take smaller and smaller subrectangles of the lamina, because the density is going to be, the density at a point can be approximated, can approximate the density over a subrectangle if the subrectangle is very, very small. So it makes pretty good sense. And of course, as we take more and more subrectangles, we have to let K and L go to infinity, and so this total mass becomes a double integral. Okay, so that would be how you find the total mass for over a lamina. Are there any questions so far? All right, well, we'd ultimately like to find the center of mass for the lamina. How many maybe have studied center of mass, have seen center of mass before in one of their courses? Okay, Noreen's seen that, Abdullah's seen that, Lexi's seen that. Absolutely, absolutely. And, you know, what is the center of mass? Well, geometrically speaking, the center of mass for a lamina is what they're showing you in figure 4. It's the balance point over which the lamina will balance. Okay, if you put a fulcrum and with a tip on it and place the lamina on that point, which is X bar comma Y bar in figure 4, the lamina balances on that point. Now, of course, if we're allowing, you know, what's going to affect how the lamina balances on the point? Well, the density is going to affect at what point the center of mass is, because you know, if one side of the lamina is heavier than the other side, that's going to affect where the balance point is, where the center of mass is. But also, in addition to where the heaviness is or the lightness is in the lamina, you also have to think about, well, okay, how far away is the heaviness or the lightness of the lamina? You know, I mean, basically, think of like two people on a seesaw, right? And they're playing on the seesaw, right? So let me just draw a little picture here. I'm not a great artist, but I'll just do my best here. All right, so, you know, here's a seesaw. Okay, let me just extend this a little bit. Okay, and let's say there are two kids, all right? I'm just gonna, here's kid 1. Okay, and here's kid 2. Okay, and on the seesaw, these kids, one kid's going to sit on one end of the seesaw, and the other kid's going to sit on the other end of the seesaw. So I actually think I didn't draw this quite right. Hold on, let me do this better. Let me do this better. One moment. Let me see here. This just, one moment. Let me see if I can. One moment. We'll see if we can get this. Picture's not the way what I want actually. Hold on. Let me just try to fix it here. Hold on. Yeah, that's not, picture isn't what I want. This is what I want. Okay, so that's better. So one kid's going to sit on one end and the other kid's going to sit on the other end. And, you know, I got a little kid, kid 1, and I have a big kid, kid 2. So for this seesaw to balance on that fulcrum point, would kid 2 be on the left or on the right? Where would kid 2 have to sit? On the left or the right? For the seesaw to be exactly like that, exactly balanced and horizontal. You've all been on a seesaw, right? Yeah, that's right, Norina. The big kid, kid number 2, is going to be sitting on the left. And kid number 1 is going to be sitting on the right. Okay, and this here, now this is just a one-dimensional. This is your center of mass. Give me a thumbs up if this is making sense to you, if this jives with what you've learned in maybe other classes. Give me a thumbs up. Okay, good. Yeva, Abdullah, and Norina are comfortable with that. Lexi's comfortable with that. Good. So what affects the center of mass? What's involved in finding the center of mass? Well, it's not just the mass of the 2 children. Then also it's how far away they are from, you know, in other words, the center of mass, what determines it is the mass of the kids. But then for the seesaw to balance, you have to be concerned about finding the right distances that kid 2 and kid 1 will sit, you know, apart from each other. You see, so I always think about that when I think about what I learned here for the lamina, because yes, we know how to find the total mass, but also we need to, hold on here, we need to worry about what are called moments, about axes. Hold on, I'm going to have to get my email off. I don't know why I'm getting stuff here. Hold on. Let me get my email off here. I don't want any interruptions. So because you're dealing with a lamina, the lamina, you have to concern yourself about, okay, you know, how the mass is distributed throughout the lamina, but also for every point of mass, how far is it away from the x-axis, and how far away is that piece of mass from the y-axis. So the moment then involves the moment function about the x-axis, m sub x, it's almost the same as the mass definition. It just you're inserting a y sub ij there. In other words, what determines, like for if you're trying to find in regards to the moment about the x-axis, what matters is how far away points are from the x-axis. So a moment about the x-axis in regards to the lamina, what matters then is not just the mass of the points relative to the x-axis, but also how far those points are away from the x-axis, and those would be distances, y distances, up and down distances, because you're measuring from the horizontal x-axis. On the other hand, if you are thinking about then the moment about the y-axis, well, there, the y-axis is the vertical axis in the xy plane, and so you're looking then at points relative to how far they are from the y-axis. That would be a horizontal distance, and that's why they insert an x in there in the Riemann sum. And so now, as you take the limit of these two Riemann sums for the moment, maybe I can highlight it here. As you take the Riemann sums of these two limits, you get these double integrals. And those double integrals then are for the moments. So now how do you find the center of mass? What you do is like if you're looking for the x-coordinate for the center of mass, what you do is you take the moment about the y-axis and divide by the total mass. And for the centroid or center of mass for the y-coordinate, y sub r, you take the moment about the x-axis and divide by the total mass. Okay, so this is really an extension of the seesaw example where you're working in one dimension, but the extension's the same. I mean, what I mean is you're just doing an extension. Has anybody, I don't know if you would have seen these in another class, but finding the center of mass of a lamina, but it's an important application of a multivariable calculus. Simon says he thinks he might have seen it in physics. Yes, and we can go even further and talk about moments of inertia, but I don't want us to, we're learning I want to try to do applications that are hopefully somewhat common sense, even if you haven't had physics, and we're not going to delve too deeply into the physics, but we are going to be learning things that you will see in physics and engineering and hopefully have an intuitive feel. So now that we have all these nice formulas, let's look at an example. Are there any questions? Okay, let's go to an example then. Okay, let me give you a moment to copy this example down, class. Okay, so in this problem, we have a lamina that occupies the part of this disk, okay, which is a circle of radius 1. It occupies that part of the disk in the first quadrant. We want to find the center of mass of the lamina if the density at any point is proportional to the square of its distance from the origin. Okay, now let's say you had a problem like this on your next exam, exam 4, right? Well, of course, in order to use to find the center of mass, and we need to utilize the formulas given in section 12.5, but what do we need? What do we need in order to do that? What do we need to find? What don't we formally have here? Well, we don't have this. This is your density function. We denote it by the Greek symbol rho. Okay, that's what the density, and you saw that in the formulas. The Greek symbol rho is your density function. So we have to come up with the density function. And we're told that the density at any point is proportional to the square of its distance from the origin. Based on that information, we can come up with the density function. So when they say is proportional, okay, is proportional, okay, that means is equals, and then what are we going to put next? What are we going to put after the equals? The density is proportional. You remember? Well, let me ask you this. It's proportional to the square of its distance from the origin. So you have a point with coordinates x, y. The distance from the origin, well, okay, what's the distance formula? X minus 0 squared, square root of x minus 0 squared plus y minus 0 squared. But it says the square of the distance from the origin. So we're going to have to take this distance and we're going to have to square it. But there's still something missing. What has to go where in front of, like right after the equal sign? Because they say the density at any point is proportional. What has to go here? They're not saying, that's right, good, Norina, a K. K has to go there. They're not saying the density equals the square, the density at any, they're not saying the density at any point is equal to the square of its distance from the origin. They're saying the density at any point is proportional to the square of its distance from the origin. So you must have this K here. You must. You must. All right. Well, are there any questions so far? Okay. Well, now we have our density function, and now we can proceed forward to working through the problem. So, okay. On the next page, I've drawn the lamina. Okay, I've drawn the lamina. And so This is my region D. Hold on. I don't want to. No, I don't want to do that. Hold on. Trying to make it look a little nicer. This quarter circle is my region D. And my density, which is a variable density because it changes as X and Y changes, the density is equal to K times X squared plus Y squared. Okay, let me give you a moment to. Now, what I've done, incidentally, is I've drawn in some grid lines at X equals a half and Y equals a half, because it's going to be a little helpful later for you to see, for when we find the center of mass, it'll be helpful. Okay, trust me, it will. Okay, let me let you get caught up to here, and please ask me if you have any questions. Here's our mass function. And again, that if you look in section 12.5, the first formula, that's the first formula. The double integral over region D, where the integrand is the density. So a lot of times, like probably in earlier classes, maybe even high school, you dealt with constant densities. But when the density is allowed to vary, depending on what part of the lamina you're on or you're located, that's more realistic, right? Because well, it's just more. It allows for more possibilities. Let's put it that way. So what we have to do now is we have to integrate this double integral. Okay, are there any questions before I go to the next page? Okay. So I chose to use polar coordinates, and I'll mention this before. So again, at this stage, okay, because I'll just show it to you. Because I have, region D here and I have DA here, I'm not committed to what, am I going to integrate with respect to rectangular coordinates or polar coordinates, right? So I'm not committed to that yet because I'm worried about, getting the density function and just, getting my double integral set up here. But now I go back and I look at region D, and region D is a quarter of a circle. Well, if region D, if the lamina is a quarter of a circle, would you recommend using rectangular coordinates or polar coordinates? What do you think the best choice is? That's right, Arian. Definitely polar coordinates, most definitely. So, okay. All right, so what would based on that, this region here, what's the radius go from? If you think of coordinates, polar coordinates throughout the region, the radius goes from 0 to 1. That's right, Lexi. That's right, Aaron. And what about theta? What about your angle theta? That's right, Aaron. That's right, Lexi. 0 to 90 degrees. So theta, beginning theta, ending theta, 0 to pi over 2. So, okay, then now that makes sense. So we are going to use polar coordinates. And of course, r d theta is the dA. That is your unit of area. And I know I'm going to iterate the double integral, so why not just put the iteration in, you know, the two iteration symbols in right away. Now this K here, we don't know what K is, okay? They just said the center of mass of the lamina, they're just saying the density at any point is proportional to the square of its distance from the origin. So they haven't given us any initial condition that would allow us to solve for K. So we have to just leave K as it is, and hopefully it'll resolve itself later. So since K is a constant, you know, K here is some constant. Well, I can pull K out in front of the integral. But this integral here, the integral of r cubed dr from 0 to 1, is some number, right? It's some value. It's a number. It's a value. So we can bring numbers out then, out in front of the outer integral, which was with respect to theta. And so that's what I chose to do. So essentially, this double integral can be expressed as a product of two single integrals. Now, this can't always be done, but in this case, we can do it. And we work it out, and we end up getting a mass of pi times k over 8. Are there any questions? We found the total mass now, but what do we have to find next? We found the total mass. The total mass is equal to pi times k divided by 8, the total mass of this lamina. What do we need to find next? Okay, Mary, the center of mass, and to get the center of mass, though, we need to find what? That's right, Norina, the moments about the x-axis and the y-axis. So now that isn't going to be too hard because the limits that we used for the double integral for the to find the total mass, we know we've found out what those limits are, and we can just use them again. So for the moment of the lamina, about the x-axis, well, this is the definition, but it makes sense. It makes sense. We understand why it's that. Because if we're trying to determine balance of the lamina about the x-axis, how far points are from the y-axis. No, how far points are from the x-axis. Let me just hold on. I'll just put a little picture here. You know, hold on here. So, you know, if this is the x-axis, then how far points are from the x-axis is important in determining that moment. And the distance is going to be a value of y, right? So, yeah, okay. So that's why, you know, the y is here. And that gets multiplied by the density. And now y in polar coordinates equals r sine theta. And then x squared plus y squared, of course, is r squared. Okay, and so you end up getting this double integral. Now, what I decided to do was that constant k can be pulled out of the inner integral and the outer integral. So I just brought it out front here. I just chose to do that. I chose to do it a little differently this time around. So go ahead and just copy the steps down. Please let me know if you have any questions. I don't think there's anything here that you wouldn't normally understand, but if you have any questions, let me know. Okay, now just see here. So, okay, check one thing. Pull this up a little bit. So, of course, negative cosine of 0 is like -1, and cosine of pi over 2 is 0. So 0 minus a -1 is a 1, times k over 5 is k over 5. Give me a thumbs up when you're ready to go to the next page. Okay, Narina's good, Arian's good, Matthew's good, Yeva's good. All right. All right. Well, now we're going to find the moment of lamina about the y-axis. But what I did was, so like the y-axis, I'll just draw a little picture here. You know, here's the y-axis. Y-axis. And if we think about points, you know, in a lamina from the y-axis, how far away are they from the y-axis? Well, that is an x distance, right? That's a distance x. And so, sorry, I'm trying to draw the best I can. It's a distance x. So that's why we have the x inserted there. Hopefully that helped. Does that help give you a little bit of an intuitive feel for what's going on? I hope it does. And it's not just the density of the point that matters. It's where, I'll say it the right way. How would the point have to be adjusted so there's balance from the axis? Well, the distance from the axis matters. That we would, so, I don't want to say too much. I think I've explained it, at least, I think I've explained it reasonably. And the practice will help a lot. So, okay, so we end up getting then this double integral, but I didn't compute it. You can show that the moment about the y-axis is also going to be 1/5 k. So then if we want to find the center of mass, what we do is we take these moments and divide them by the total mass. So if we want, for the centroid or center of mass, if we want the x-coordinate, we have to take the moment about the y-axis and divide by the total mass. And when we do that, the beautiful thing that happens is these k's, remember the constant of proportionality k, we didn't know, right? We didn't know what that, we don't know what that is. But the k's simplify out. And so x bar is 8/5 pi. Now this is the answer that WebAssign is going to want, but I'm writing 8/5 pi as a decimal because I want to go back to the picture and point out where x bar is. So 8/5 pi as a decimal is 0.5093. For y bar, for the y coordinate for the center of mass or centroid, we take the moment about the x-axis and divide by the total mass. And again, here, those k's simplify out. Okay, and we're going to get 8/5 pi, or 0.5093. So it's really quite amazing. The x bar and y bar coordinates are the same, and for the center of mass. And it has to do with the density function. The density at any point on the lamina is proportional to the square of its distance from the origin. And we are restricting ourselves to the, well, we're in the first octave, or the first quadrant. So are there any questions? questions on these values here? Well, let's go back to the picture and just plot the centroid approximately, or the center of mass on the picture. So hopefully it can make good sense. So let me go ahead and clear the annotations here. So there's the lamina at the top, and essentially it's about at a half-half. Okay, where that center of mass is. It's right about here, right? Center of mass. So in terms of the, if I were to, I don't want to be careful not to have things too thick, but if I were to like draw just a line segment from the origin to the edge of the lamina, and the center of mass, maybe I'll put it in red so it shows up a little bit better right there. The center of mass in terms of like, you know, distance from the origin, okay, the center of mass, if you think about the distance that the center of mass is from the origin and compare it to the distance that that center of mass is from the boundary of the lamina, it's closer to the boundary of the lamina. Okay, it's closer to the boundary of the lamina. So just want to see if that makes sense to you. It might be better to think about it actually. If we look at those, let me just erase this. Hold on. I'm just trying to think about it. I mean, here's the center of mass right here. It falls above the halfway mark in regards to the x-axis and the y-axis. And the density, as you might note, and its center mass is fairly close to the edge of the lamina. But as you move away from the origin, the center of mass or the density gets greater, right? So I want you to have an intuitive feel for why that center of mass is where it is. Okay, you know, it's not there for a reason, right? It's not here. It's not there for a reason. And it has to do with how the density function is defined. Okay? Are there any questions on this before we stop the recording? Who's feeling good with this example? Okay, Aura's good. Wonderful. Let's put center mass here. Noreena's good. All right. And hopefully, intuitively, this makes sense. Abdullah's good and Yeva's good. It's always easier when you have a constant density to intuitively feel comfortable about why the center of mass is where it is on the lamina. But hopefully this makes some sense. Okay, great. Well, if there are no questions, I'll go ahead and stop the recording. Okay.